Okay, good evening, everyone. Today I'm going to talk about duality in linear programming. Okay. Can I see? Okay. And the dual problem is another LP problem which can be directly defined from the original LP problem, original primer problem. Okay? And both primer and dual problems are closely related to each other, so that the optimal solution of one problem automatically provides the optimal solution to the another problem. Right? And this screen shows the symmetric primer and dual pair, and it has some characteristics such that if the primer LP is n by n, which means it has m different constraints, not including non-negativity restriction, and n variable, then in dual problem you should have n constraints and m variables. Okay? And going back to the computer screen, just note that the AT, A superscript T, represents the transpose of the matrix A. Okay? This one. Let me get the highlighter. So I'm talking about this A transpose matrix compared to this A matrix. Okay? And for every variable in the primer problem, there is a corresponding inequality constraint in dual problem. And for every inequality constraint, there is a corresponding dual variables. Okay? And the right-hand side vector of the primer problem, which is B, serves as the objective function coefficient vector of the dual problem. And the objective coefficient of the primer problem serves as the right-hand side of the dual problem. Okay? Okay, then let's take an example for this. The primer problem is a minimization problem with greater than equal constraints, right? While the dual problem is a maximization problem with less than equal constraints. And the objective coefficients of the primer problem serves as the right-hand side vector of the dual problem, right? And conversely, the right-hand side of the primer problem serves as objective coefficient of the dual problem. Okay? And to every constraint in the primer problem, there corresponds a dual variable, right? Which means if you have two constraints in the primer problem, then there should be two decision variables in the dual problem. Okay? And to every variable in the primer problem, there corresponds a constraint in the dual problem. Okay? That is, if you have two decision variables in the primer problem, then there must be two constraints in dual problem. Okay? Of course, both primal and dual problems include sign restrictions on each decision variables. Okay? Okay, then in the symmetric primal dual pair, minimization problem has greater than equal constraints and non-negativity restrictions, right? Now, let's suppose we have an inequality reversed in the primal problem. Then, how do we write the dual of this problem? First, we must transform the problem. We multiply the offending inequality by -1, thereby reversing the direction of the inequality can be performed. Right? Now, the problem is in the form of the primal, in the symmetric primal dual pair, right? Therefore, we can write this dual problem like this. Now, it's interesting to make a change of variable. Let's set y1 prime equals -y1. Okay? Then it's same as dual of the symmetric primal dual pair, except for non-positivity, replacing the non-negativity restriction. Is that right? So you remember in the symmetric primal dual pair, maximization problem has less than equal constraints and non-negative variables. Now, if I substitute negative y1 for y1 prime, if I substitute negative y1 for y1 prime, then the dual problem looks like this. So we can notice that the reverse direction of the constraint in the primal problem corresponds to the reverse direction of the variable in the dual problem, right? In the symmetric primal dual pair, the minimization problem has greater than equal constraints and non-negative variables. Now let's suppose rather than an inequality constraint, we have an equality constraint.
Before that, so the standardization, how are we going to do that? That y1 prime is less than 0. So can we handle using the negative value handle the problem?
Which one?
Here, before this line.
This one?
Yeah, that y1 prime less than 0.
Right.
So can we solve the problem with that?
Of course, you need to convert. Probably you can substitute for, let's say, g equals negative y1. Yeah, then you can solve this, right? Because, as I know, all the optimization solver packages, they assume all the decision variable is greater than equals, right? Unless it is specified otherwise, okay? But at this time, I just show you how to convert the primal problem to the dual problem, okay? Thank you. Okay, now let's suppose rather than an inequality constraint, there is an equality constraint, okay? Then we will see how the dual problem looks like. So first, we need to transform the inequality constraint into the equality constraint, right? And then multiply the offending inequality by -1 so that the direction of the inequality can be reversed. So our problem in the form of the primal problem in the symmetric primal dual pair is like this, right? Now we can write a dual problem. We have chosen to name our dual variables, not y1, y2, and y3, but y1 prime, y1 double prime, and y2. Because the first two constraints in the primal problem come from only one inequality constraints, right? And notice that the pair of dual variables, y1 prime and y1 double prime, always appear with opposite signs. Okay? Now let's substitute y1 for y1 prime minus y1 double prime. Okay? Here we note that we cannot include a constraint on the sign of y1 variable, because it is the difference of two variables, which is y1 prime minus y1 double prime, right? This is the same as the dual and the symmetric primal dual pair, except for the missing non-negativity restriction for y1 variable. Is that right? So the dual problem looks like this. Now we can notice that equality of the constraint in the primal problem corresponds to the unrestricted in sign of the variable in the dual problem. Okay? Okay, then now I'm going to show you the dual of the dual problem is the primal problem. Okay? Okay, then how do we write the dual of problem? How do we write the dual of the dual problem? Okay? First, we must write it as a minimization problem with greater than equal constraints. Okay? In here, problem D is equivalent to problem D prime. Okay? Minimizing the negative of a function is the same solution, except for sign, as maximizing the function, right? Also, the negating both sides of a less than equal constraints produces a greater than equal constraint, right? And the dual of the problem D prime is problem D double prime. Is that correct? The objective coefficients of the primer serves as the right-hand side of the dual problem. Likewise, the right-hand side of the primer problem serves as the objective coefficient of the dual problem, right? And the problem D double prime is equivalent to problem P, because again, maximizing the negative of a function is the same solution as minimizing the function, except for signs. So, given a primal dual pair of LP problem, it is arbitrary which one is referred to as a primer and which is referred to as a dual. Okay? And the dual of an LP may be found by first rewriting the LP in the form of one of the LPs in the symmetric primal dual pair. On the other hand, the dual can be written directly for any LP using this relationship. Okay? Okay, then let's take an example. Let's construct a dual problem given the primal LP like this. Because the primal problem has three constraints right now, right? Which means the dual problem must have three decision variables, right? So let's say y is the dual problem. Y is the dual variables. Okay. Likewise, because the primal problem has only two variables, which means the dual problem must have two constraints, right? And the primal problem is maximization problem, so dual problem must be the minimization problem, right? We have three decision variable, y1, y2, y3, and we have two constraints, right, in dual problem. Okay. The first row is objective function row. The next two rows are the two constraints of each. Next, the objective coefficient of the primer serves as the right-hand side of the dual problem, right? So the right-hand side, so the objective coefficients are 3, 5 in the primer problem. So the right-hand side value in dual problem becomes the transpose of this value. So let's say the right-hand side value is going to be 3 and 5. Okay? Next, the right-hand side vector of the primer problem serves as the objective coefficient vector of the dual problem, right? And in the primer problem, the right-hand side vector is 4, 12, 18. So the objective coefficient in dual problem becomes the transpose of this vector. Okay? So it's going to be 4, 12, and 18. Is that right? And the coefficient values of the constraints in dual problem is the transpose of the constraints coefficients in the primer problem. So currently, the constraints coefficient matrix in primer problem is A, which is 1, 0, 0, 2, 3, 2, right? So in dual problem, A transpose matrix, which is 1, 0, 3, 0, 2, 2. A transpose matrix becomes the constraint coefficient in the dual problem, right? So it's going to be 1, 0, 3, 0, 2, 2. Okay? And because there is no negative coefficient values, we have plus sign here. The given primer LP problem is in the form of dual problem in the symmetric primer dual pair, right? That is, the primer problem is maximization problem with less than equal constraints and non-negativity restrictions, which means its dual problem must be a minimization problem with greater than equal constraint and non-negativity restrictions for all of the decision variable. Okay? So this is our dual problem. Let's take another example. Well, I think I'd better write down here. Okay, this is the primal problem. So as you can see here, the primal problem has only 3 decision variables, which means in your problem we will have 3 constraints. Likewise, in primal problem we have 1, 2, 3, 4 constraints. That means in your problem we will have 4 decision variables. Is that right? And so if I say y is the dual variable, then our dual problem would be y1, y2, y3, and y4, right? Because we will have 4 decision variables in the dual problem. And I said we will have 3 constraints in dual problem. And next, in primal problem, objective coefficients are 4, -1, and 2. So the right-hand side value in dual problem becomes the transpose of this value, right? So in dual problem, right-hand side value becomes 4, -1, and 2. And the primal problem, we have 5, 7, 6, 4 as the right-hand side value. And the transpose of this value becomes the objective coefficient vector in the dual problem. So it becomes 5, 7, 6, 4. Okay? And in primal problem, the A matrix, the constraint coefficients, so the 1, 1, 0, 1, 1, 0, 2, 1, 0, 0, 2, 1, and 1, 0, 1, right? So the A transpose matrix becomes the constraint coefficient in the dual problem. Okay? So in dual problem, oops. Okay, this is right. Constraint coefficient would be a transpose matrix, which is 1, 2, 0, 1. 1, 1, 2, 0, 0, 0, 1, 1, right? 1, 2, 0, 1, 1, 1, 2, 0, 0, 0, 1, 1. Now, we need to determine the sign restriction of each decision variable and the form of dual constraints. To do that, we need to use this table. Okay? So let's go back to the computer screen. Thank you. Or I think I'd better write down, because I'm going to back and forth a couple of times more. Max, min, type of constraints, less than equal, greater than equals, sign of variable greater than equal unrestricted in sign less than equals. Okay. The minimization problem is sign of variable greater than equal unrestricted in sign less than equal. And type of constraint is greater than equal, equal, and less than equal sign. Okay? Okay, so in the primal problem, the first constraint is less than equal sign, right? And our primal problem is maximization problem. So in the maximization problem here, first constraint is less than equal sign, right? Which is this. Which tells us in minimization problem, the first variable should greater than equal 0. Okay? So the first dual variable is greater than equal to 0. Okay? And in maximization problem, which is the primal problem in our case, second constraint is also less than equal sign. Again, in maximization problem, second constraint is less than equal sign, which means in minimization problem, the second variable should be greater than equal to 0. So y2 variable must be greater than equal to 0. And in our primal problem, which is maximization problem, the third constraint is greater than equals sign, right? So in maximization problem, third constraint is greater than equal sign, which means in the minimization problem, the corresponding decision variable should be less than equal sign. That's why the third decision variable should be less than equal to 0. And in the maximization problem, the first constraint is equal sign. In maximization problem, the first constraint is equal sign, which means in minimization problem, the corresponding decision variable should be unrestricted in sign. So the last decision variable in dual problem, which is y4 variable, should be unrestricted in sign. Okay? And in the maximization problem, in our primal problem, the first decision variable, x1, is greater than equal to 0. In the maximization problem, first decision variable is greater than equal to 0, which means in minimization problem, the first constraint should be greater than equal to equal sign. Okay? So first constraint should be greater than equal sign. In maximization problem, which is primal problem, the second and the third variable is unrestricted in sign. In maximization problem, second and third variable is unrestricted in sign, which means in minimization problem, second and third constraint should be equality. Okay? So we have equal sign in here. Okay? So this is the dual problem. Okay? Isn't that easy? Now you know how to use this table. Okay? To convert from maximization problem to minimization problem, or vice versa. Okay? And again, just tell you, either of them can be the primal problem or dual problem. Okay? So if maximization problem is your primal problem, then the dual problem must be minimization problem. Likewise, if the primal problem is minimization problem, then your dual problem must be maximization problem. Okay? Okay, then let's take another example. At this time, we are given a minimization problem with primal problem. And we'd like to construct a dual problem. Okay? Because this given LP problem is in the form of the primer in the symmetric primer dual pair, right? Which is minimization problem with greater than equal constraints and non-negative variables. Which means its dual problem must be a maximization problem with less than equal constraints and non-negative variables, right? So its dual problem would be like this. Is maximization problem. And because in primal problem we have two variables. In dual problem we have two constraints, right? And in primal problem we have three constraints, which means in dual problem we will have three variables, right? So it's going to be y1, y2, y3. And the right-hand side value is 413, so it becomes the objective coefficient vector. And the objective coefficient vector in primal problem is 1, -1. This becomes the right-hand side vector in the dual problem. Right? And must be like this. And a transpose matrix becomes the constraint coefficient, which is 2, 1, 1, and 1, 1, 2, right? And all the decision variables, y1, y2, y3, must be greater than or equals 0, right? What about next example? This is again the minimization problem. So we are required to construct the maximization problem, right? Because the primal problem has three constraints, the dual problem must have three decision variables. So let's say y1, y2, y3. And the primal problem has four decision variables, which means the dual problem must have four constraints, right? y1, y2, 4 times, and y3, again, 4 times, okay? And the objective coefficient in primal problem is 635. Well, actually is 6305, right? Okay, thank you. 6305 becomes the right-hand side values, in the dual problem. And in primal problem, the right-hand side values are 20, 30, and 50. It becomes the objective coefficient values in the dual problem. So 20, 30, and 50. Okay? And in primal problem, the A matrix constraint coefficient, so the 1, negative 2, and 4, 2, 1, 0, negative 1, and this we have 0 up here, 0, 5, 1, 1, right? Which means the A transpose matrix, which is 1, 2, 0, negative 2, 1, 5, 4, 0, 1, 0, negative 1, becomes the constraint coefficient, the dual problem, right? So let's just fill in those values. 4, 0, 2, 1, 0, negative 1, 0, 5, 1, 1, right? Now we can use the table to determine the form of dual variables, the sign restrictions of dual. The form of the dual constraints, the sign restrictions for each dual variables, right? So again, use this table. First, in primal problem, which is the minimization problem, the first constraint is less than equal sign, right? So the minimization problem, the first constraint is less than equal sign, which means in maximization problem, the first constraint is less than equal sign, is down here, right? Which means the maximization problem, the first decision variable must be less than equal to 0. So y1 variable is less than equal to 0. And in the primal problem, in minimization problem, the second constraint is equal sign. In minimization problem, second constraint is equal sign here, which means in the maximization problem, the corresponding decision variable is unrestricted in sign. So y2 variable is unrestricted in sign. And in minimization problem, in our primal problem, the third constraint is greater than equal sign. Third constraint in minimization problem is greater than equal sign, which means in maximization problem, the third variable must be greater than equal sign. Okay. And in primal problem, which is the minimization problem, the first and third variable is greater than equal sign. Right? In minimization problem, the first and third variable is greater than equal sign, which means in maximization problem, the first and third constraint should be less than equal sign. Okay? So first constraint and third constraint should be less than equal sign. And in our primal problem, the second variable is unrestricted in sign in minimization problem, which means the second constraint in the maximization problem should be equality constraint. And lastly, the fourth variable, x4, in minimization problem is less than equal sign, which means the maximization problem, the fourth constraint should be greater than equal sign. Now we've completed the dual problem like this way. Okay? I believe we've practiced a lot. So I assume how to use this table to convert the minimization problem to maximization problem, or vice versa. Okay? Okay, now I'm going to talk about the economic interpretation of the dual problem. To illustrate the economic interpretation of the duality, let's reconsider the window glass example, which has been covered early this semester. So in this example, window glass makes two products, doors and windows, in three different plants, right? That is, the production time required for door is 1 hour and 3 hours at plant number 1 and number 3, respectively. And for windows, 2 hours of production time is required at each plant number 2 and 3. And plant number 1 is available for 4 hours per week, and plant number 2 for 12 hours per week, plant number 3, 18 hours per week. And the profit per door is $3,000, and the profit per window is $5,000. And this given information is summarized in this table. So to formulate the mathematical linear programming model, we begin by defining the relevant decision variables, right? So in any linear programming model, the decision variable should completely describe the decisions to be made, right? And the manager in this company must decide how many doors and windows should be produced per week, right? So we define two decision variables, x1 and x2, which represents the number of batches of product number 1 and number 2, which is doors and windows produced per week. And once we define the decision variable, the next step is to determine the objective function. And for this problem, our goal is to maximize the profit. So if you let the capital G is the total profit per week from producing these two products, then our objective function would be maximize 3,000 times x1 plus 5,000 times x2 equals z, right? And we also need to determine if the values of each decision variables are limited by any restrictions, which is called constraints, right? According to the problem description, each batch of doors produced per week uses only 1 hour of production time per week in plant number 1, whereas only 4 hours per week is available. And this restriction is expressed mathematically by the inequality. x1 is less than or equal to 4. So we have x1 is less than or equal to 4 as a constraint. Likewise, plant number 2 imposes the restriction that 2x2 is less than or equal to 12. And for plant number 3, we would get 3x1 plus 2x2 is less than or equal to 18. And finally, because the production rate cannot be negative, it is also necessary to restrict the decision variables to be non-negative, right? The dual of the window problem would be like this. The first dual constraint is associated with the first primary variable, which is about door, right? And the second dual constraint with the second primary variable, which is about the window, right? And the y1 variable, the first dual variable, is associated with plant number 1 hours, okay? Which is the first primary constraint. And the y2 variable with plant number 2 hours, and y3 with plant number 3 hours, right? Now we are ready to interpret the window dual problem. Suppose you start your own business. So you are an entrepreneur and you want to purchase all of Windows resources. Then you must determine the price that you are willing to pay for a unit of each of Windows resources. So to determine these prices, we define y1 variable, which is the price paid for 1 hour of labor at plant number 1, okay? And y2 variable is the price paid for 1 hour of labor at plant number 2. Likewise, y3 variable represents the price paid for 1 hour of labor at plant number 3. Okay? For your problem. And the resource price y1, y2, y3 should be determined by solving this dual problem, right? The total price that should be paid for these resources is 4 times y1 plus 12 times y2 plus 18 times y3. And because the cost of purchasing the resources is to be minimized, the minimized W is the objective function for the window dual problem. Okay? And in setting resource prices, the prices must be high enough to persuade window to sell. So for example, you must offer window at least $3,000 for a combination of resources that includes 1 hour of production time at plant number 1 and 3 hours of production time at plant number 3. Because the window could, if it wished, use these resources to produce a door that could be sold for $3,000 later on. And because you are offering y1 plus 3y3 for the resources used to produce a door, window must choose y1 and y3 to satisfy y1 plus 3y3 is greater than or equals to $3,000. Okay? Likewise, at least $5,000 must be paid for the combination of resources used to produce a window. So y2 and y3 must satisfy 2y2 plus 2y3 is greater than or equal to $5,000. And the second restriction, y1, y2, and y3 variables are greater than or equal to 0, must also hold. The solution to the window dual problem is the prices for labor hours at plant number 1, 2, and 3, right? And the dual problem, and the dual theorem tells that the primal problem and the dual problem have equal optimal objective function values. Of course, if the problem have optimal solution, okay? Okay. Then now let's reconsider the symmetric primal dual pair. Okay. Suppose that the x hat is feasible in the primal problem and y hat is feasible in the dual problem. Then the weak duality theorem tells that the Cx is always greater than or equal to By. In words, the weak duality theorem tells that the objective value of minimization problem is always greater than or equal to the objective function value of maximization problem in symmetric primal dual pair. Okay? Okay, then let's take an example for weak duality theorem. First, we're going to construct the dual problem for this and use weak duality theorem to show that the optimal solution for the primal problem has z, which is less than or equal to 0. Okay. Okay, first let me write down our primal problem. Okay. There is maximization problem. So first, we can see that the given LP, given primal problem, is in the form of the dual, in the symmetric primal dual pair, right? Which is, it is the maximization problem with less than equal constraints and non-negative variables, right? Which means the dual problem must be the minimization problem, right? With greater than equal constraint. Okay? And non-negative variables. Okay? And because the primal problem has two constraints, in dual problem, we will have two decision variables. And in the primal problem, we have three decision variables, which means in dual problem, we will have three constraints. In primal problem, right-hand side values are 12 and 1 becomes the objective coefficient. And the objective coefficient in the primal problem is -1, -2, and -1. So it becomes the right-hand side value in the dual problem. In primal problem, constraint coefficient, which is represented by capital A, is 1, 1, 1, 1, 2, -1, which means A transpose matrix, which is 1, 1, 1, 1, 2, -1, becomes the constraint coefficient, the dual problem, right? 1, 1, 2, 1, 1, negative 1. So we've completed our dual problem. So it's pretty easy to convert from the primal problem to the dual problem, right? Okay, now we need to answer for the second question. It asks us to use the weak duality theorem to show that the optimal solution for the primal problem, which is less than or equal to 0. Okay? So, if you look at the objective function, the dual problem, the dual objective function value, W, will be improved, which means the objective function value will be decreased, because this is the minimization problem, right? If both y1 variable and y2 variable decreases, right? Because both of them has positive coefficient. Is that correct? And the lower bound of y1 and y2 variables is 0, right? From the sign restriction. And the value zero, zero, the origin does satisfy all three constraints, right? Because 0 is greater than or equal to negative 1, and 0, 0 is greater than or equal to negative 2, 0, 0 is greater than or equal to negative 1, right? So which means y1 equal to 0 and y2 equal to 0 is the optimal dual solution. Is that correct? And with this value, y1 equal to 0 and y2 equal to 0, the dual objective function value becomes 0. Is that right? And the weak duality theorem tells that the objective function value of minimization problem is always greater than or equal to the objective function value of the maximization problem, which is our primal problem, right? Of course, those two, minimization and the maximization problem, should be in the primer, in the symmetric primer and dual pair. Okay? So this G value should be less than equal to the W value, which is the objective function value from dual problem. Right? And we've known that W should be equal to 0, right? So we are able to show that the optimal objective function value for the primal problem should be less than or equal to 0 using the weak duality theorem. Okay? Okay. Any questions? Okay, this is all for today. And next time, I'm going to continue to talk about the duality, okay, with several more example problems. Okay? Okay, thank you. I will see you next time.